Good morning, everyone, and welcome. My name is Jennifer Nyman. I'm with Geosyntec Consultants in Oakland, California, and we are the coordinator of the webinar series on behalf of SERDP and ESTCP. Today, we will first have a brief overview of SERDP and ESTCP, and that will be followed by two technical presentations on advances in stormwater monitoring, management, and treatment at DoD facilities. First, Marianne or Molly Colvin will discuss improved methodology for laboratory toxicity testing associated with stormwater events. Her presentation will be followed by a question and answer session. Then Richard or Dick Luthi will present on rapid flow engineered filter media for treating stormwater runoff. His presentation will also be followed by a question and answer session. We will conclude the webinar today with a question and answer session featuring both of today's speakers. The next few slides provide some instructions on optimizing the webinar. If you haven't done so already, download Zoom at the link shown here and provided to you in your webinar registration email. If you cannot download Zoom, you can view the slides using an internet browser like Firefox, IE, or Edge, and by creating a free Zoom account. If you are unable to view the slides or if your screen freezes, you can try keying Control with F5 to perform a hard refresh. If you are accessing the audio through your computer and have any issues with the audio, click on the arrow next to the Join Audio button and select Test Speaker and Microphone and follow the prompts. If you continue to experience any audio difficulties, please call into the conference line, which is shown here. You may also submit a comment using the chat box for technical difficulties, but please keep the chat function for those comments related to technical difficulties. The Q&A option should be reserved for questions. In case of continued technical difficulties, you can download a PDF of the slides from the webinar webpage and then call into the conference line. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link that is shown here at the bottom of this slide. Today's broadcast will be listen only. You can submit questions by using the Q&A box on your screen. You don't have to wait until the question and answer period to submit your questions. And in fact, we encourage you to submit questions in advance of that session. When you submit a question, please add your organizational name at the end of your question. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of SERDP and ESTCP, as well as the Program Manager for the Environmental Restoration Program area. Dr. Leeson has been with SERDP and ESTCP since 2001. Prior to that, she was a research leader at the Patel Memorial Institute, where she conducted research on in-situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea.
Thank you, Jennifer, and thank you to everyone who has joined our webinar today. Before we get started, I'd like to just give you a very brief overview of who we are and why we are doing these webinar series. We are a companion program made up of SERDP, the Strategic Environmental Research and Development Program, and ESTCP, our Environmental Security Technology Certification Program. SERDP is our science and technology program. We've been around for about 30 years now, and it is a partnership between DoD, the Department of Energy, and the Environmental Protection Agency. And this is our traditional R&D program. And as technologies or knowledge matures, it graduates moves into ESTCP, where we demonstrate and validate technologies in the field. And under ESTCP, this is where we're really looking to transition these technologies out of the lab and to develop the field information we need to see that the technologies lead to commercialization or broader adoption. Now we have a few environmental drivers that really help us craft the sort of research programs we have. The first is that we are focused on the sustainment of our testing and training ranges, our facilities and operations. And as you can imagine, this means it's pretty broad, the sort of things we cover, everything from maritime sustainability, changing environment, unexploded ordnance and munitions constituents in the environment, as well as a number of other issues. We also are looking at reducing current and future liabilities. This falls under our traditional pollution prevention program, where we're looking to eliminate hazardous chemicals or materials, processes in our manufacturing, maintenance, and operations. And then we also are dealing with contamination from past practices. This can include the large UXO liability, different emerging contaminants, and all of these impacts on groundwater, soils, and sediments. And the projects you'll hear presenting today fall under this area of dealing with these past practices. We have a number of different focus areas then. Shown here, we have a large program dealing with issues associated with installation restoration. And again, the presentations you'll hear today fall under this area. Of great importance to the program is then the technology transition, and we do this in a number of ways, and all of this we make available on our website. We have a number of different guidances and manuals that are available. We do in-person training when we're able to, videos. We have developed a Wikipedia-like page with all of this environmental technology summaries that we've developed. And then finally, we have this webinar series that we use to transition the technology out to end users. If you go to our website, you can find all of the upcoming webinars that are in the future. And most importantly, I think, is you can also get archived versions of these webinars. So if you have missed any, you can go back and you can get all of the audio and video from these past webinars as well. You can go to this page to get that information, and you can also register for the upcoming webinars at this link. I would also like to point out that we have our annual symposium coming up. Symposium is probably the best way to get information about everything that SERDP and ESTCP is funding. This year we are going with a virtual event. The registration is open, so I hope this does make it easier for everyone to participate in our symposium. So at this point, I'd like to turn it back to Jennifer to introduce our speakers.
Great, thanks, Andrea. So now I'll introduce our first speaker, Molly Colvin. She is an aquatic toxicologist and manager of the Naval Information Warfare Center Pacific Bioassay Laboratory, which is in San Diego, California. She conducts basic and applied research in support of improved site characterization and management of contaminated discharges, surface waters, and sediments, with a focus on understanding the bioavailability and toxicity of DoD-relevant contaminants to biota. She received a bachelor's degree in ecology from the University of California, San Diego, and a master's degree in ecology from San Diego State. Molly, please proceed.
Hi there, everyone, and good morning. Thank you for that introduction. I just want to start out by thanking SERDP ESTCP for the support on this project and facilitating this webinar. And again, my name is Molly, although you may have seen my formal name is Marion, and sorry for any confusion, but I do go by Molly. So my project is entitled Interlaboratory Calibration Comparisons for Post-Exposure Toxicity Testing. And I'm going to be referring to ICS for Interlaboratory Calibration Study for short, so you might see that come up a few times. So to start, my presentation is going to follow the outline as shown with my project objective, the methods and results that came from this ICS study, and then I'll follow with conclusions, DoD benefits, and finish up with acknowledgements. So typical stormwater monitoring, such as what we do here in Southern California, where I'm located, requires end-of-pipe sampling collected during the first few hours of rainfall or discharge. And then the samples are then evaluated with laboratory toxicity tests using a continuous exposure to the organisms for up to 7 days, depending on the species and test endpoint that's being used. Now, when that methodology does not adequately replicate the exposure conditions that are either at the point of compliance or as it mixes with the receiving environment. For example, these pictures on the right-hand side were taken at Naval Base Coronado here in San Diego, California. And the top picture is San Diego Bay on a given Tuesday back in January 2019. And the middle and bottom pictures are an outfall where stormwater sampling took place less than 24 hours later. And the typical monitoring requirements for stormwater would require sampling of these discharges at the onset of the event. And then those samples are taken back to the lab for chemistry and toxicity evaluations, with exposures lasting up to 96 hours of continuous exposure or 7 days, just depending on the species and test endpoint. However, storm events are rarely, they rarely last 96 hours, especially here in San Diego. And less than 24 hours later, for this example, sunny conditions were seen again. And the sample that was taken no longer is representative either at that point of compliance where the sample was collected, nor in the receiving environment. So the dynamic nature of stormwater discharges that might be experienced in a marine receiving environment cannot be accurately reflected using current EPA standard toxicity test methods. So our project team has developed and refined a pulsed exposure toxicity test method for multiple species. So under current standard methods, as represented by the image on the left-hand side, using static whole effluent toxicity samples, the organisms are exposed to that sample for a continuous time period. Under the pulsed exposure method, organisms are exposed for reduced time periods to the effluent or stormwater sample, and then for the remainder of the exposure period, the organisms are exposed to clean laboratory or receiving water, and that's done by transferring them into the clean seawater or receiving water with mesh screens or tubes. And these methods will assist users to conduct these pulsed exposure tests for evaluating episodic or ephemeral discharges, such as the stormwater runoff that we test here in Southern California quite frequently. So the first aspect of our project consisted of a series of experiments that derived baseline data for pulsed exposure toxicity testing using multiple species and toxicants. So for our tests, we evaluated chronic embryo larval development tests using purple sea urchins and acute survival tests using the marine mysid shrimp and the freshwater flea and amphipods. Copper, zinc, and the organic bifenthrin were tested in triplicate for each of these species for 6, 12, and 26-hour pulsed exposures. And these exposure durations, these pulsed exposure durations were selected based off of an extensive rainfall and discharge analysis that was conducted as part of this project. Now, all of these pulsed exposure tests that we conducted in the laboratory were also run concurrently with standard methods for direct comparability of the results. Following all the laboratory derivation studies, we did some verification studies where we took our methods and used them on real stormwater samples that were collected alongside of regulatory monitoring testing that was being conducted at Navy region bases. So we also did field demonstrations that verified that the pulsed exposure methodologies were representative and protective of actual site conditions during these dynamic runoff events. So we were able to use concurrent in situ toxicity testing with the sediment ecotoxicity assessment ring, or C-ring, which was a technology that was developed under ESTCP as well. And these in situ tests were performed at these adjacent to the outfalls that were being evaluated for stormwater toxicity. And the C-ring served as a platform for exposing the same species that are being used in the laboratory, and we were also able to expose those same animals in the receiving environments adjacent to those discharges. So these samples were collected and tested also in the laboratory and done and conducted with the pulse exposure method and the static method. So all said and done, we had lab-based and field-based toxicity samples to really provide that connection between what's being observed at the end of pipe and what is being experienced by the organisms in the receiving environment. So just a quick snippet on some of the data that we received from the lab and field-based exposures for our validation studies. So shown here is the results of our in-situ exposures with the sea rings with the chronic test using purple sea urchins, and this was in San Diego Bay in 2019. The percent normal development for the organisms is shown on the y-axis, and the sites and depth of deployment of the sea rings is shown on the x-axis. Now the red line at 80% shows where the threshold would be observed for significant toxicity for this species. And ultimately what you can see is that these organisms were deployed throughout an entire storm event, and no toxicity was observed in the receiving environment for these organisms. These results, and I apologize for how small they are, but these are the laboratory exposures for two different sites for the same species. And what you can see is on the left-hand side is also the percent normal development, and along the x-axis for both of these figures is the exposure duration, so the pulsed exposure durations and a slightly modified concentration series that was tested. And the red line, again, indicates the threshold for toxicity for this species. Now, the red box that is shown on each of these figures is the sample that would be used for monitoring purposes, for what is reported to the regulatory agencies. This is 100% sample that is exposed to the organisms for a continuous exposure. And you can see with this species, we saw complete toxicity associated with these samples. However, the results to the left of each box are for the pulsed exposures. And these results show greater frequency of abnormal embryo development with increasing effluent exposure with both duration and concentration. And these results highlight the dynamic and complex exposures that might be experienced in a marine receiving environment that can't adequately be reflected using these current static standard EPA test methods that were originally developed for continuous point source discharges. And the in-situ exposure shown in the previous slide provide the basis for comparison and show that standard end-of-pipe exposures overestimate the toxicity that is observed in the receiving environment, in particular for this highly sensitive chronic sea urchin test. So now on to the meat and the good stuff of this project was to conduct a comprehensive interlaboratory calibration study, or ICS. And the methods that we followed to conduct this study were modeled after an EPA interlaboratory variability study conducted for whole effluent toxicity testing, for short-term testing. The pulse exposure SOPs that were developed through this project were distributed to qualified labs across the US and to a lab in Canada to assess the ability of the proposed pulse exposure methodology to provide consistent and defensible data for monitoring of these episodic discharges. The samples were prepared and distributed to participating labs for blind testing, and the labs were instructed to perform both standard and continuous exposure testing, as well as the pulse exposure testing for, the pulse exposure testing was for 26 hours. Three wet methods were evaluated as part of this interlab calibration study, and they include a freshwater cladoceran, the Seriadaphnia dubia, and two marine species, the mysid shrimp, Americomyces bahia, and the purple sea urchin, Strongylus centrotus purpuratus. So in total, we had 12 laboratories that were involved with the study. 7 labs were with the freshwater flea study, 8 with the mysid shrimp, and 7 labs with the purple urchin test. Not all labs could perform all methods. And so we ended up with about 7, 8, and 7 for each of those test exposure or test methods respectively. Each participating laboratory was required to pre-qualify for each test method by documenting their capabilities, experience, and proficiencies, and their quality assurance processes in order to meet the needs of the study. So there was a very comprehensive evaluation of each lab prior to the start of this. The study characterized these performance metrics listed here, which include the completion rate, false positive rate, precision, and repeatability. And false positive rate is an indicator if a sample was not supposed to be toxic, but a laboratory found that sample to be toxic, that would be a false positive. Precision was evaluated by looking at the coefficients of variation for different endpoints for each of the test methods that we evaluated. And repeatability was a comparison of duplicate samples. So samples 4 and 5 of these blind samples were both positive controls and duplicates of each other, which were just spiked laboratory seawater with copper. So I'm going to be going over this first method for the Cereodaphnia dubia in a little bit more detail, and then I'll skim over the other 2 species, just so for time's sake. And so first, the data from 7 labs was generated for the Cereo test, and test acceptability criteria was met for all tests and all data that was deemed acceptable. The false positive rate for this species was 0% for the laboratory control water. And as an additional analysis, we also looked at if there was any false positive rates for the non-toxic stormwater sample that was evaluated as well. And for both the pulsed and standard methods, we did have a lab for each one of these methods find this sample, one sample to be toxic. So for each of those methods, pulsed and standard, we had a 14.3% false positive rate. So precision was estimated through the analysis of coefficient of variation, as I mentioned, and in this case, we looked at the point estimate. So the lethal concentration at which 50% of the organisms experience mortality, or the LC50, we were able to generate a coefficient of variation for that and look at that. We are only able to generate the LC50 for this series of tests for the pulsed exposure testing. So the LC50 that is shown here is only for the pulsed exposure method. But for comparison purposes, to be able to look at the pulsed exposure method versus the standard method, we looked at the CVs of the 6.25% concentration for each of the samples that were tested. And then we pooled those results and averaged them. And we're able to see that the CVs for pulsed exposures was 28.7% and the standard method was 39%. So that is nice to see that there is some comparability between the 2 methods, or between the pulsed and the standard method. And then finally, an evaluation of repeatability was performed, as I mentioned, on those 2 duplicate samples, and no significant differences were observed in those samples. What is nice is that looking at the data can be better interpreted by these figures. And what you're looking at here is the LC50 concentration on the y-axis, which is that lethal concentration at which 50% of the organisms experience mortality. And on the x-axis are the blind samples. So sample 1 is the laboratory control, sample 2 is that non-toxic stormwater sample, sample 3 is a toxic stormwater sample, and 4 and 5 are the duplicate positive controls, or the copper spiked control waters. And what we're looking at here is ultimately is very tight data. However, what happens is when you have relatively low LC50 values for these 3 samples, a small change in response can lead to elevated coefficients of variation. So that's when you look at the coefficient of variation that I reported on the previous slide of 67.2, it just, by nature of the statistics, the coefficient of variation gets driven up when we have such low responses such as these. And that factor should be accounted for when interpreting this data. And shown here is a figure that is looking at that repeatability. So this is where we are comparing the duplicate samples, number 4 and 5, the positive controls. And again, this figure shows that the duplicate samples for each laboratory, which is shown on the x-axis, they are very close to one another. They are very comparable. And to evaluate these statistically, we looked at paired sample t-tests, and which showed no significant differences between sample 4 and 5, indicating good comparability in results between those two samples. So just kind of, I'm going to show the data real quick for the mice and shrimp. We have even tighter data associated with the shrimp. We had 8 participant labs. We had 100% completion rate, no false positives associated with those control samples. And our precision is much lower. And if you look at the precision of that 6.25% concentration, they're extremely low, which is gives us a lot of confidence in laboratories' abilities to perform the pulse exposure method relative to the standard method. And showing the data again here for variability, we have the box plots that show the LC50 concentrations across all the labs. And again, this is very tight. And we are very excited for the data that we've been able to generate. And the comparisons of the duplicate samples. And again, for this, there were no significant differences in the duplicate samples when we looked at paired t-tests across all of these samples. And similarly with the urchin test, we had 7 participant labs. We met all test acceptability criteria. We had 100% completion rate. There were no false positives on either test method. And similar to the Stereodaphnia test, the precision or the coefficient of variation for the EC50 in this case, the effective concentration at which 50% of the organisms experience abnormal development, was 55.4%. And again, this is due to the fact that we had low responses or low EC50s, and when you have small changes in those EC50s, it drives that coefficient of variation up. So we look at the 6.25% concentration for comparability between the pulsed and the standard method. And in this situation, the pulse method was had higher precision than the standard method. And no significant differences were observed in the duplicate samples. So again, you can see here, these are the EC50 concentrations for the urchin test. And with those EC50 concentrations being so low, it just tends to drive that coefficient of variation up when we are making those analyses. And again, this is the comparison of those duplicate samples. And again, no statistic differences were observed in the paired t-tests in these. Oops, sorry. So in summary, when we look at all 3 methods combined, we have 100% completion rate, and we are very excited that we were able to do this interlab calibration study across multiple laboratories during the COVID pandemic, right at the onset of when everybody was getting locked down, and I'm very pleased with how everything turned out. Our false positive rate, when we look at all 3 methods combined, the negative control had 0 false positives, and it was only in those couple Stereodaphnia non-toxic stormwater samples where we did see a couple false positives. Precision, and for simplicity purposes here, I'm just showing it for the 6.25% concentrations. The pulsed exposure method had a lower coefficient of variation than the standard method, but fairly comparable. And for the repeatability, we were able to look at the relative percent differences, and they were all below 20% for each species evaluated. And as I mentioned previously, no significant differences were observed in any of the methods for those duplicate samples that were tested. So all in all, we have shown that the pulse exposure method was very comparable across multiple laboratories and was similar in the metrics evaluated to the standard method. So in conclusion, throughout this project, we have discussed with a variety of interested parties, which have agreed that the objective of this project, that an alternate method for evaluating episodic discharges is warranted. It is justified and needed. The pulse exposure approach is easily understood and a feasible approach to assess short-term exposure conditions, as this method incorporates just simple modifications to those existing wet methods. And the in situ data that I showed previously showed that the receiving water, where the beneficial uses are and where organisms actually reside, were non-toxic or low in toxicity despite the dynamic conditions that are occurring during stormwater runoff events. This helped drive the need for a more representative toxicity testing approach in the laboratory. So currently, the pulse exposure method is being integrated into multiple monitoring programs, such as a Navy Region Southwest Stormwater Monitoring Program, as well as monitoring programs for dry dock discharges up at Puget Sound Naval Shipyard. And so for both programs, this additional line of evidence allows us to better understand the effect that magnitude and duration of these effluent samples may have on the organisms being tested. And in both instances, the results of these pulse exposure methods are being communicated back to the respective regional water quality control boards as part of their reporting requirements. So with that, this project has been a very large effort, and I would like to thank my project team members listed here, my coworkers, Gunther Rosen and Nick Heyman, Chris Dransky from Wood Environment and Infrastructure, Dr. Tom Wong from Loyola, Mr. Bryn Phillips from the UC Davis Marine Pollution Studies Lab, Ms. Adrienne Seaboard from Enthalpy, Dr. Howard Bailey from Nautilus Environmental, and Dr. Jerry Diamond from Tetra Tech. I would also like to acknowledge that this is a leveraged project with the Navy's Environmental Sustainability Development to Integration Program, or NESD, under project number 547. And I would also really like to thank all the participant laboratories for the interlab calibration study who made this happen while we were all experiencing the lockdown and still experiencing it in a few ways. And with that, I'd like to say thank you for your time, and I appreciate the opportunity to share some of our work.
Wonderful. Thank you, Molly. And at this time, I would like to remind our audience that you may submit questions for Molly based on her presentation using the Q&A button, which would show up at the bottom, usually the bottom of the Zoom platform on your screen. We do have a few questions for Molly. First, can you say more about how this method is incorporated into permit-based monitoring, or how it could be more extensively incorporated in the future?
So as I mentioned, the current methods that we're employing as part of that tech transfer is to conduct side-by-side testing along with regulatory monitoring that's already going on. And this helps us generate an additional line of evidence to understand the impacts a discharge may have on that receiving environment. And so it helps us rule out the duration aspect of a given discharge, because these discharges, especially in San Diego, they just never last 72, 96 hours. I mean, the rainfall analyses that we conducted as part of this project, the 95th percentile of rainfall duration that occurs in the San Diego region is only 26 hours. So being able to perform this pulse exposure method with more realistic durations that are reflective of actual storm conditions gives us that additional evidence to understand the duration aspect and how it impacts the receiving environment. So we are conducting these tests side by side with standard methods and communicating this to the regional board when reports are submitted.
And as a follow-up, what has the response been from the regulatory agencies so far about these data and results? And has EPA, the United States EPA, been involved?
So part of the project, our first task was to generate an advisory panel that would help us not work in a black box and allow for continuous communication of the work that we are doing and the results that we are observing. And there are a few members of EPA on that advisory panel, and they have provided great constructive criticism of the work that we're doing, and they understand the justification and the need for an alternate method, and we are working with Region 9's Office for Alternative Test Protocols, or the ATP method. So we are looking at trying to submit these methods for formal EPA review and acceptance. It's just a matter of time of getting all of our ducks in a row to be able to submit it. But again, on our advisory panel, there are a few EPA members from Office of Research and Development. And then we also do have a local regional water quality control board member who is on the panel that we've been communicating the results of our work to. And they've been receptive. I think everybody's just trying to figure out what is the best way for implementation and how do we bring this to the actual end users for use in their monitoring program. So we're working on that.
Okay, wonderful. And also just to follow on that, we had a comment from the audience noting some uncertainties in quantitative toxicity estimation. It's dependent on species, the endpoint, the exposure conditions, the storm that's sampled. So would all of those uncertainties support a more conservative method, like the 96-hour static exposure test, or are you seeing that those uncertainties can be accommodated with the pulse testing?
Well, with whole effluent toxicity testing, you are testing the whole sample, so that what is being tested in standard methods, the sample that's being tested is also, it's the identical sample. We're just slightly adjusting the duration of exposure, but ultimately we wanted to generate some baseline data, and the laboratory studies that we conducted were only for a few constituents and for only a few species. So I think that something that could be developed further, looking at other species and how they perform, and some considerations that need to be made with regard to variability, such as the timing of that pulse exposure or any latent effects that might be observed. And some of these considerations were addressed and in our project as part of that leverage project with our NESG. So if anybody is interested in looking at that final report or some of the publications that we put out that address some of these considerations of variability associated with species or endpoints, we can, I'd be glad to share that and talk about that further.
Okay, wonderful. And are you looking to apply these methods to other contaminants other than the metals in this study? Do you think that's something that down the road?
Well, we looked at, for the interlab calibration study, it was only primarily metals were the driver in this situation. As part of the original laboratory studies where we were generating baseline data, we did look at bifenthrin as another contaminant. And some of our collaborators have been looking at a few other metals and other species as well. So it's out there. We are ultimately, at this time, we are not looking, but it is something that I could be convinced to do more of down the road.
And then a question about the source that you tested. Recognizing that source area can influence toxicity level, was the stormwater source that you tested urban, was it agricultural, and was it from a vehicle trafficked area?
The stormwater sample that we tested for the interlab study was from it was not a high-risk industrial area. I believe it was stormwater runoff from like a urban road area, like within the city of San Diego. It was an opportunistic storm that we were like, oh my gosh, we need rainwater, let's go get it. And in reality, the sample was fairly non-toxic, and so we had to make some adjustments to that sample in order to make it a little bit so that we were able to generate a dose response for each of the species that we were testing. So there was a lot of preliminary testing that we did with that stormwater sample prior to distribution to the laboratories.
Okay. And Molly, we just have one final question for you. Would you please summarize for us the best way to evaluate variability across the laboratories and maybe summarize the results from this study with respect to the comparison across the laboratories?
So ultimately, the way that we were analyzing the variability across the laboratories was looking at the coefficient of variations of the dose responses that were observed. And this was modeled after the EPA's intra-laboratory variability study that was conducted in 2001. So we were modeling our analyses after what EPA did for their study. However, in the situation that we ran into where we had the dose response that we saw resulted in very low EC or LC50 concentrations, such as for the cereals or for the urchins, when those values get very low, it tends to drive that coefficient of variation up. And it's just by the nature of statistical analyses. And so that's why we decided to start looking at individual concentration response in our scenario. And that seemed to be the best way for us to be able to evaluate whether a lab was able to perform it and how the comparison across laboratories was evaluated.
Okay, wonderful. Thank you so much, Molly, for the excellent presentation. And to the audience, Molly will come back online at the end of the webinar to address a couple more questions. So at this time, I'd like to introduce our second speaker today, who is Dr. Dick Luthi, a professor of civil and environmental engineering at Stanford University in California. And he is the director of the National Science Foundation Engineering Research Center for Reinventing the Nation's Urban Water Infrastructure, or Renew It. And that center seeks more sustainable solutions to urban water challenges. Dick's research addresses organic contaminants and contaminants of emerging concern in both engineered and natural systems. He is a member of the National Academy of Engineering. He earned master's and doctoral degrees in civil engineering at the University of California, Berkeley. Dick, please proceed with your presentation.
All right, thank you, Jennifer. And hello, and thanks for attending this webinar. So the subject of this discussion is rapid flow engineered media to prevent sediment contamination from stormwater. What I'll do today is talk about stormwater management in a more general sense and the importance of it and what some of the co-benefits might be when we manage stormwater, and then talk about our project objectives and methods and results, show some modeling of contaminant transport to predict longevity of these engineered stormwater control measures, describe a potential field study, and conclude with some benefits to DoD. So stormwater management is really important, and the subject of the work here and the focus of it was to prevent sediment recontamination. And as you may imagine, DoD has lots of challenges with maintaining sediments and waterways and bays and estuaries and like that clean, and there's remediation taking place. But once that's done, we want to make sure that that we're not recontaminating an area that's already been cleaned up. And so for that, we're looking at how to treat stormwater to prevent sediment recontamination. But along with that, there are these other objectives that take place, like we're protecting water quality, protecting beaches and harbors, which is so important. DoD, like other entities, have to comply with MS4 permits, stormwater permits. So in the process of complying with MS4 permits, there's the opportunity to do a better job and to think about other benefits that might come along with an improved stormwater control measures. And one important one is the ability to capture and use stormwater. This is really important. It's of interest to the EPA and the Water Reuse Action Plan, and of course, many others in water scarce regions. And the co-benefits can come also with design of control measures that have park-like features and green space. So the issue here with stormwater management is not just sediment recontamination, but looking at this other picture of how can we manage our stormwater, capture, treat, and then use it for water supply. And out here in the West, we're in a drought, though in Northern California, we might get a heavy rain this weekend, but still, essentially the western part of the country, and particularly the Southwest, has been experiencing a drought for a long time. And this stormwater capture and use then provides an opportunity to augment our water supplies, most likely by recharge into the ground. And so as we do that, we also, at the same time, prevent sediment recontamination. Here, the business case for stormwater management with the view towards contributing to water supply is very cost effective. Larger stormwater control projects might cost on the order of $500 per acre foot of water captured. An acre foot is about 1/3 of a million gallons. Here where I live, the wholesale price of water is $1,800 per acre foot. So stormwater capture can be done at something like 1/3 to half the price we're currently paying for wholesale water prices. And in 8 years, that wholesale water price in our area will go up to about $2,800 an acre foot. These compliance with MS4 permits requires that we do infrastructure investment. So as we're doing that, we should keep an eye out for the co-benefits and think about, is there an opportunity to do something with the stormwater other than just discharge it? And stormwater control measures and co-benefits are very popular with the public and regulators. So that brings us to the sort of subject of the discussion today, that how can we improve stormwater control measures, and how can we capture contaminants to prevent sediment recontamination, and also perhaps augment water supplies as well. But stormwater contains a whole mix of contaminants from pathogens, urban use biocides, some that we just heard about from Molly, vehicle-related compounds and such. So there are quite a few compounds, not necessarily at extra high concentrations, but more in the range of microgram per liters and less. But collectively, you have quite a few contaminants present. So in our work, what we're looking at are the ways to improve the performance of stormwater control measures, And we're looking at media mixtures and filter performance and long-term tests. And we're looking at how biochar, a particular kind of biochar that we've screened, a high temperature gasification biochar, can be used beneficially, and also regenerated activated carbon. Both of these materials, the biochar and the regenerated activated carbon, have a low carbon footprint. We'd like to derive parameters for modeling and design, and then demonstrate value to DoD users. So the idea here is that for a stormwater control measure, you have a controlled flow of stormwater through a engineered media filter. I call these rapid flow engineered media. Rapid flow meaning on the order of 20 to 60 centimeters per hour. And this would require then that there be an outlet control, and that we would look at sorption that would be enhanced by these black carbonaceous materials. Now, to make this work, you would need an hydraulic buffer. In other words, a detention pond of some sort, or a way to just a way to control the flow through these filters. And the idea would be that if a storm is predicted to come, you could run whatever water is in your hydraulic buffer through the filter a little bit quicker to draw down the hydraulic buffer, let it fill during the storm, and then treat again during the non-storm period. And our work here then is to look at the effectiveness of these materials for a suite of contaminants at these higher flow rates, and conduct long-term studies to where we can get some information to predict the effectiveness over many pore volumes. So our methodology here involves a partnership with Naval Weapons Station Seal Beach, which is located just south of Long Beach. And we collected with their assistance catch basin material from the wash rack and wharf drains, had that shipped back up to our laboratories, and then mix that to make synthetic stormwater that we could use in long-term testing. We add dissolved organic carbon to our matrix mix, extract from straw-like materials. It's important to have the DOC there because that can interfere with the performance of sorbent materials. And then we add a suite of organic contaminants, a number of about 20 comprising both hydrophilic and hydrophobic compounds. And our interest here is primarily in the hydrophilic compounds, the ones that are more water soluble, and the ones that are more problematic than in not being captured. Hydrophobic compounds tend to associate with particles, and they can be removed by settling or just a coarse sand filter. So in our work, we're looking at these suite of organic compounds, hydrophilic compounds comprising herbicides, insecticides, 2 munition compounds, and corrosion inhibitor, and hydrophobic organics, some PAHs and PCBs, and some insecticides. We also have added perfluoro substances as well, making some perfluorochemicals addition here from aqueous film forming foams, AFFF. The hydrophilic compounds are added at 40 micrograms per liter in our test. The hydrophobic compounds around 100 nanograms, and PFAS compounds around 10 micrograms. And in this AFFF mixture, the predominant compound was PFAS. So these hydrophilic compounds are the ones that show in the blue circle here, have the lowest tendency to sorb and the greatest water solubility. And those are the ones that would be least likely to be removed in a conventional stormwater control measure. So our methodology here being done with graduate student Conrad Pritchard at Stanford and graduate student Kat Mills at Colorado School of Mines is to conduct a whole series of laboratory flow-through tests with multiple solutes at once. So this is sort of a stress test where you have all these chemicals at once and also at relatively high concentrations that you probably would not see in stormwater. These tests are conducted in triplicate, and we have controls with sand only, and then other mixtures with biochar and regenerated activated carbon, and we've used zeolite as well in some of these tests. So the idea here was to run the stormwater flow through the columns for a period of time, like over 360 pore volumes, and then do a challenge test with about 1,400 pore volumes, and then do a final flushing experiment. So the challenge test would be the one where you add these trace chemicals. The total run for one of these experiments is about 6 months. This is the experimental apparatus shown here that's set up at Stanford. So let me show some results now. And this shows experiments from the column studies where we have sand and zeolite, regenerated activated carbon, and biochar. Now, we're using a relatively low weight percent of biochar and regenerated activated carbon, about 2.4% biochar and about 3.3% weight percent of activated carbon. And the reason we're in the low range here is because we actually wanted to see transport through these columns. In reality, you might use more biochar or activated carbon. But what the data show here, if you just focus on the blue and the black, we see that for these mixtures that contain either the regenerated activated carbon or the biochar, there's no breakthrough over 500 empty bed volumes here. You can just read across from the top, the benzotriazole, the atrazine, the diuron, fipronil, imidacloprid, and the mecaprop. So there's very good removal here, even at these low weight percent of biochar or regenerated activated carbon. Well, when we do the test, we can measure within the column near the inlet and the halfway point to see if chemicals are migrating down the column. And that's what's shown here in this slide, reading from left to right. The column effluent with atrazine, and then at the 50% port with atrazine, and the 25% port with atrazine. So this media depth was 60 centimeters, so this would be like at 15 and 30 centimeters. And so what we see here in the effluent again with the atrazine, there's no breakthrough. But then when we go up to the halfway point in the column or the 1/4 point place in the column, you start to see this migration now of the atrazine. So the atrazine is sort of moving through the column as a front. A wave of concentration is making its way through the column. Well, we can use these data then to estimate sorption properties of these chemicals, and then from that we can do modeling. So looking at 6 illustrative compounds here, if we look at the halfway sample port, this is with 20 centimeters an hour, reading this list of contaminant, mecaprop is moving the fastest, fipronil next fastest, atrazine is somewhere in the middle, and then imidacloprid, diuron, and benzotriazole are really not moving at all. So this is the kind of data that we can use to estimate sorption parameters for modeling. What I'll show now is that work for the compound atrazine. The reason I pick atrazine is kind of in the middle range of these different compounds. So the way we do the modeling then is we invoke a one-dimensional advection dispersion equation with interparticle diffusion limited sorption. Now, basically what that means is we have advection by the water flow, we have dispersion, and we have sorption within these sorbent media, the biochar or the regenerated activated carbon. We can get pore water velocity. That's a controllable factor in our experiments. Dispersion coefficient comes from tracer studies like a bromide tracer. But the retardation coefficient or sorption term here requires that we do examination of the transport data to back out the sorption coefficients, which are tortuosity, and then these Freundlich isotherm coefficients, Kf and 1/n. And we can do that looking at, say, the 25% port data, and then say, well, how well does that fit the 50% port? And how well does that, what might we see at higher flow rates, for example? So this shows fitting for model parameters. Again, atrazine, 25% port, 20 centimeters an hour phase velocity. And from this, we back out the Freundlich coefficients and the tortuosity factor. And then and the black dots here are the data extending over 1,500 hours. And the dashed blue line is our predicted breakthrough. Now, our predicted breakthrough, this includes real-time flow and effluent concentration variation, which you can imagine in a long test. Even though we're trying to hold it constant, there are issues with fluctuations in concentration of compound and in delivery of the flow rate. So the blue line shows what you would get if you, with real-time flow and influent concentration, but there's some damping of that in the column itself. So this is the way we derive these sorption parameters. And now we can ask the question, well, how well does it really fit the other data? So this shows fitting the data for taking those sorption coefficients and now looking at what we see at the 50% port. And the fit is quite good. And again, this is with atrazine. We're here at 40 micrograms per liter in the presence of that whole suite of compounds, including the dissolved organic carbon. And we see that the prediction works quite well. This shows now what happens when we increase the flow. So that previous data was 20 centimeters an hour. What if we double it to 40 centimeters an hour? And this shows the data for atrazine again, here at the 50% port in column effluent, now with twice the flow. So we're not readjusting, we're not changing the sorption parameters, keep them constant. The only thing we're changing here is the flow rate. And again, it fits the data well. Then this next slide shows boosting now to 60 centimeters an hour. Now, 60 centimeters an hour is the upper range that you might actually put through a stormwater control measure. That's about 2 feet an hour, roughly. And what do we see here for atrazine again? Well, we have a very good fit with the 50% sample port and the column effluent here. So all of this looks really good, and we can use our modeling now to make predictions. Like, well, what happens if I had a lesser concentration? What if all the contaminants were present, not say at 40 micrograms per liter, but more like 1 or 4? And also, what if I were to boost the weight percent of black carbon? What would we expect to see then? Well, that's shown here in the next slide, where the plot on the left shows a filter depth of 1 meter, biochar content of 3%, a flow rate of 20 centimeters an hour. But now looking at predicted atrazine behavior at concentrations that range from 40 to 4 to 1 or 0.4 micrograms per liter. Now, if you look at stormwater monitoring, atrazine concentrations in stormwater, upper range might be a microgram per liter or a bit more. So with that thought, you could see, well, we could treat perhaps thousands of bed volumes, 5,000 to 10,000 bed volumes. Now that's with 3% biochar content. What if we were to increase the biochar content? And so the plot on the right now shows predictions with 1% by weight, 3% by weight, 5%, and 10% by weight. Now biochar is not very heavy, and so when you get about 5% by weight, you're getting close to a filter that has a lot of biochar in it by volume. And our consultant on the project, Scott Struck with Geosyntec, cautions that you'd like to be able to mix some sand, coarse sand in with these materials to maintain the hydraulic performance. So, somewhere maybe 5 to 10%, that would be the most we'd ever put in a actual facility. But what does that tell us? It says, well, we could treat, again, something like, well, up to maybe 10,000 empty bed volumes. That's a long time. So what we are looking at here now is the next stage of this work would be to do a field study. And here's a picture of Naval Weapons Station Seal Beach. The left figure with that green arrow shows stormwater discharge onto the naval station. That stormwater flows through this vegetated channel and into these culverts that you see on the left. And then that water is conveyed in these concrete channels across the base and then eventually discharged. There's opportunity here to do a large pilot test and parallel test to assess the effectiveness of these modified filters actually in the field. And at Naval Weapons Station Seal Beach, there's the space to actually do this. And our partners there, Jeff McGovern and Rich Wilson, are interested in seeing this work go forward. So this is an example of a place where we could go to the next stage. So our conclusion here then is that the regenerated activated carbon and high temperature biochar are effective for stormwater contaminant retention. I want to emphasize we've demonstrated performance here under under worst case conditions. We have all the solutes present at once. We've done our modeling with all this the solutes present at once, and we have a relative high concentration of dissolved organic carbon in the range of 5 to 10 milligrams per liter as carbon. So what we've demonstrated here is the potential for the stormwater capture and treatment and beneficial use possibly, like for water supply. And these kinds of approaches are gaining popularity with the public and regulators. And what the benefits to Department of Defense is improved stormwater management strategies for removal of contaminants from runoff, the prevention of recontamination of surrounding aquatic sediments and surface waters, beach protection and that sort of thing, just like Molly showed there at San Diego, an area surrounded by beaches. Same thing at Naval Weapons Station Seal Beach. And then with our modeling, we can optimize removal based on some target contaminants and whatever climate conditions there are with respect to stormwater runoff. And so the long-term performance modeling allows us to make some predictions about operations and what kind of maintenance might be needed in terms of replacement of the filter media. We think at a place like Naval Weapons Station Seal Beach, where they get on the order of 11 or 12 inches of rain a year. If you devoted 1% of your area to a filter, you could run one of these filters for maybe 5 to 10 years before you'd have to replace it. But that estimate is predicated on the fact that you have controlled flow to the filters and that the filters are not acting as particle removal devices, because that would result in clogging. So I'd like to acknowledge our partners here. Conrad Pritchard, PhD student at Stanford, who's been with this work from the beginning. Yomyang Cho, research engineer here at Stanford. At Colorado School of Mines, Kathleen Mills and Chris Higgins are helping with the perfluorochemical analyses. And our consultants here at Geosyntec, Scott Struck, has been advising on this work and on what we should be thinking of going to the next stage. And Geosyntec will also be preparing a guidance document based on our work. And I think that's the end of the talk here. There's some references that you can get later from download, and there's contact information. So I'm ready to answer any question, Jennifer.
Great. We do have a number of questions, and to the audience, if you would like to submit any additional questions, please do that now using the Q&A box. First, Dick, could you say more about why you added dissolved organic matter to the influence matrix when DOC isn't a contaminant itself necessarily? And then the second part of that is whether in climates with autumn leaf drop, if that would provide a natural source of DOC.
Well, the answer to the second question is exactly right, that leaf drop, leaf litter will provide dissolved organic carbon. When we got the catch basin material from Naval Weapons Seal Beach, both what we saw at the site and what was shipped to us, there's a lot of straw there, and straw from the fields of, around the weapons station. And so in these stormwater runoff, you have some dissolved organic carbon. It's not toxic, but it will sorb onto biochar and to regenerate activated carbon. So you need to have that in place to assess, well, what will happen with contaminant removal under conditions in which you have other constituents present. Now, the DOC will affect the kinetics of uptake, but because these are larger molecules, they probably don't affect the overall capacity of the activated carbon, but they could affect the kinetics of uptake. Anyway, that's
Great.
Well, I'll just say having DOC in the water is very important.
Mm-hmm. Thank you. Perfect. Next, do carbon and biochar have a finite lifespan, and does that increase maintenance and maintenance costs?
Yes, they do have a finite lifespan. Now, in our studies here, we used a low percent by weight in the filters because we actually wanted to see migration. But what would happen is after a period of time, which might be measured in some years, maybe 5 years or longer, you would have to replace this material. So it does have a, you're absorbing contaminants on it, so it has a finite life. But this material has high sorption capacity, and so you can get, it will have a relatively long life. And you do have to do maintenance And I just want to emphasize again, our predictions about performance in the field look really great, but you have to have some pre-treatment to prevent clogging of your filters. In other words, these filters can't act as particle traps. If they act as particle traps, then you'll have short runs because you'll form this particle layer in your filters, and then the water won't be able to flow. So there needs to be a sedimentation basin or maybe a coarse sand filter to remove particles before it goes into this kind of device.
Understood. As a follow-up to that, you presented and then just referenced some sort of hydraulic buffer, like a sedimentation basin. Do you have any thoughts about using higher flows, like high flow biofiltration?
You mean for a pre-treatment?
Or treatment in general?
Well, high flow biofiltration, that could actually work with particle removal, but biofiltration in itself probably won't work on these hydrophilic compounds. You need a sorbent material. So if you had like an engineered swale or something like that, and the water's percolating through it, you could take that effluent and run it through one of these modified filters. So Jennifer and whoever asked the question, we're looking at compounds that are present in stormwater, that are persistent and mobile, and it's that mobility that is the challenge for, say, a bioswale or a biofilter.
Okay. Wonderful, thank you. The next question is from EPA and asks about the costing for the addition of the biochar. Could you summarize the costing that was conducted and if you have any specifics on biochar?
Oh boy, I wish I was better prepared right now because I know this from buying this material. Regenerated activated carbon is about half the price of virgin carbon. It can be bought in large quantity. The biochar now, we're not, we screen various biochars, and if you have a biochar that's produced at low temperature, it might look like biochar, but it doesn't have a very high surface area. So what we find is you need these biochars that have been produced at high temperature and from a consistent source, like a lumber mill, like Douglas fir or something like that. And in that case, you're probably talking about costs that are analogous to that for regenerated activated carbon. And by the way, again, it's important that you have a material that you can buy in quantity. And there's lots of biochars that are made in small operations, and we didn't use those types. We looked at biochar produced in large quantities and from a consistent source. I'll just finish by saying, when you buy activated carbon, you know what the source is often. It's usually made from bituminous coal. The biochar can be made from all different kinds of things. Unfortunately, you don't want biochar made from green waste that you might pick up in a city because you don't know what's in it. But biochar made from lumber waste, like Douglas fir and such, that's fine. You have a consistent source and the starting material is clean. And by the way, if folks want to get more information about our materials and stuff, you can just send a note to luthi@stanford.edu and I'll provide all of that information.
Okay, great. And then one last set of questions for you, Dick. We've received a number of questions about PFAS. Do you think that the results of your studies would apply to other concentrations of PFAS, since PFAS behavior can be concentration dependent? or to other concentrations of biochar, like higher biochar contents?
Right. So when we did our studies with perfluorochemicals, we added them as a AFFF mixture at about 10 micrograms per liter. That's pretty high, Jenny. And about half of that chemical in the mix was PFAS. And we saw a pretty good removal of the PFAS, maybe 80% removal over 500 empty bed volumes. We could do a better job with more biochar or more regenerated activated carbon. So Kat Mills is helping us with all of these perfluorochemicals analytical work, and she's on maternity leave at the moment. And when we'll have more data about that shortly.
Wonderful. Thank you so much, Dick. And we'll bring back Molly now to the questions and answers. And we have just a few more questions for each of you. So Molly, the first one is for you. Can you talk to some of the regional considerations for implementation of the new types of methodology that you were talking about?
Hi there. Yeah, so when we've been looking at implementing this method, the pulse exposure method, at these different DoD locations, we've had to make a lot of assumptions, but ultimately implementation is going to have to be on a site-specific basis, where we're examining rainfall or discharge durations for a given site, or discharge like outfall specifically. And, you know, along with that goes with surface permeability. If you've got a lot of impervious surfaces, such as what you would get at high-risk industrial sites, then your rainfall discharge analysis is a little bit more simple. Where you've got more pervious surfaces, then we tend to look at rainfall as a proxy to discharge here in San Diego, because all of our sites are high-risk industrial sites. So we get kind of a 1-to-1 ratio for what rainfall you see typically equates to the same duration for discharge. However, when you have more permeable surfaces, that may not be the case. So when you're looking at implementation of this method, you just really have to look at some of the site-specific characteristics to be able to make sure that you're addressing everything correctly.
Okay, thank you. And Dick, we have an interesting here. The audience member notes that there has been talk of reusing treated groundwater for decades, but the assumption was that it would be deemed by the end users as too risky. And you talked about what might be some changed attitudes, some interest in reuse of stormwater. So can you comment on what might be driving that change?
Well, I think it's a realization of the fact we're in a water short area of the country. And even in places that are water rich, we see interest in capturing stormwater because the groundwater systems may be overexploited. We've had workshops with the EPA on the potential and advancing the reuse of stormwater for water supply. And there's a national interest, but there's greater urgency, clearly, in places where water is scarce. Here, Jenny, you know as well as I that our stormwater has been managed for flood control, and it's conveyed to the bay or the ocean as quick as you can. And we have these concrete channels that allow that to happen. Well, that was the 20th century. 21st century is one of saying, hey, let's do a better job of protecting our beaches, our coastal environments, and taking advantage of this water that's already here, that's available, and reduce dependency on imported water, because there's going to be so much less availability of imported water for a variety of reasons, from climate change or the need to sustain environmental flows in rivers and streams. So it's a different mindset of thinking about stormwater less as a problem and more of an opportunity.
Great, thank you. Molly, a last question for you before we wrap up. Could you comment on the new methodology you talked about and whether it's more labor intensive to be implemented?
Sure. The methodology is actually a minor modification to standard methods that laboratories are already proficient in testing. So the labor aspect of it is not increased dramatically at all. I think there are some nuances depending on the species that's being tested and depending on which pulse duration you end up working with might adjust some of that. I think the potential hitch is if you decide to do a 12-hour pulse exposure, then you're going to be transferring those organisms potentially outside of normal business hours. So that might be a little bit of a hiccup for some laboratories, but all in all, we have found in our lab with all the preliminary testing that we've done that the level of effort is minimal in respect to the standard method. So.
Great. And as we wrap up, Molly, is there one last message that you would like to leave the audience with today, or one last summary statement?
I would just really like to say thank you to all the laboratories and members of our Pulse Exposure Advisory Panel and our sponsor, SERDP and ESTCP, for their support in this novel methodology that we've been working on over the past few years. I know it's a little bit outside the norm for SERDP and ESTCP on this front, so I really appreciate all the support that we've received from them.
Great, thank you. And Dick, any last statement or message?
Well, again, just like Molly, I thank the whole team on this project and the support from SERDP. This is kind of a monumental effort in terms of all the data that we've collected and the rigor with which we're designing these tests. And the last thing is that, you know, when we deal with stormwater and treatment, we do have to do maintenance. It's not install and forget. We've seen plenty of those. If you install and forget, they're just not going to work. So you have to do maintenance. And the final comment is one of think co-benefits, and I've described some here. You know, sort of a reimagined stormwater management can provide lots of co-benefits, popular with the public and popular with regulators. And again, thank you for your